Welcome to Physics with Mr. Brazil. We're looking at a torque problem, an evenly massed 110 kilogram beam that's attached to the wall, and it's 5 meters. So we have this beam that's sticking out of a wall. It has a center of mass that's down the middle because it's evenly massed, so FGCM. It also is 5 meters long and has a wire attached, and it's called massless, so it has a tension, and there's a theta. Okay, that's right between the beam and the wire. We need to determine that tension. There's also a mass hanging from it that's 10 kilograms. I'm going to call that FGM. These are applying a torque at point O, where the beam is attached. Also, where that beam is attached, there is a twisting torque that's right here, and it has a resultant, and I'm going to call it tension O, and we need to determine that resultant force and its direction. So we're going to end up using torque first, and then we're going to use the sum of forces and its component vectors. So let's get started. First task, we're going to do the sum of torques. First of all, we have the torque due to the center of mass. We need to talk about direction. Well, I always tell my students to draw a little curve with an arrow, put a dot in the middle, and tell people what the torque going into the paper or away from the paper. Is it positive or negative? So in my case, it's clockwise. I choose negative. You can choose positive, but make sure you tell people what it is. So that means tau center of mass is negative because it's twisting. If I put my thumb at point O and I take my fingers, it's going to twist in a clockwise direction. So that's negative for me. That also means that the tau due to mass is also negative. Now, when it comes to the tension, that's pointing or angling towards the wall. It's going clockwise, counterclockwise, so that's going to be positive. So tau tension is positive. And since this is at equilibrium, there's no motion, it's basically static. So in other words, it's equal to 0. So tau tension now equals positive tau center of mass plus positive tau mass. Let's write our equations for torque. So in the case of tau tension, it'll be T, R tension, and R tension is going to be equal to the full length, so that's going to be the 5.0 meters, sine theta, that's going to be the 60 degrees. So make sure you know your torque equation. You should know that. So the same thing applies now. Since the center of mass and the gravity of the mass are 90 degrees, I'm just going to write force of gravity, Cm, RCm, and RCm, the distance from point O, is equal to 2.50, not even 0, 2.5 meters, okay? And that's the distance from point O to the center of the beam, plus the force of gravity due to the mass, and that'll be, I'll call it Rm, and Rm is also equal to 5.0 meters, okay, because it's at the very end where the tension wire is tied to. Now let's rearrange this equation. So we're going to have T equals, and I'm going to factor out G, so we're going to have MCM RCM plus MM RM. I'm going to put that in a bracket. G all over RT sine theta. And let's put some values in so we can do some math. We have 110 kilograms. That's going to be times 5. Let's draw that a little better. 5.0 meters plus 10 kilograms times 2.5 meters. Let's put a bracket times 9.80 meters per second squared. Extend that. Our T is 5.0 meters sine 60 degrees. Okay. And our answer is 736 newtons. So that's the tension on the wire, but we're only good to 2 sig figs. I will be using 3 sig figs when I do my math, but 740 newtons altogether. So that is the answer for the tension. Boom, we got that using torque. Now, we have some other issues. Let's try now to find the tension on the other side. But what we're going to need to do to find at point O, we're going to need to find the tension due to the component vectors of T tension. Let me explain what I'm talking about. So, we have our wire, that's tension. It has some components. It has a component in the y direction, Ty. It also has a component in the x direction, Tx, and theta is still right here. So we need to find those component vectors to find, one to find Tx, which will allow us to find all the forces in the horizontal direction and all the forces in the y direction. Let's see what I'm talking about, okay? First, let's tackle Tx. So what's interesting, in the x direction, we have, and if we look at the drawing on the left side, we have TOX. So the sum of forces in the x direction is equal to a positive TOX minus TX, okay, from the right side, the tension wire. Again, static, so this is 0. So TOX equals TX, and TX equals T cosine theta. Well, we now know what T equals, so that's 736 newtons. I'm going to use the 3 sig figs again. Cosine 60.0 degrees, and that is all equal to 368 newtons. Okay, and that is 370 newtons to 2 sig figs. Okay, and that's our answer for Tx. Now let's tackle Ty, because from that we're going to find our resultant, TO, and then we're going to be able to find our direction. Okay, so let's change our color. Okay, the sum in the y direction now. Here's how this is going to go. We have T, O, Y. Yeah, if you look again to the left, we have a component vector, T, point O, Y. That's positive, it's pointing upward, plus Ty pointing upward from the right side, where the tension wire is at. Then we have FG center of mass plus FG mass. And again, this is all equal to 0 because it's not moving, it's static, it's at equilibrium. So, hey, it turns, oh, did I put plus? Those forces due to gravity are downward. I need to fix that right now. That's going to be minus FG center of mass and minus FG mass. Okay? Caught that. And when I saw those positive, I went, wait, everything's going to be kind of all of a sudden negative. That's not going to be good. or it's going to be it's going to make TO a greater force. Those two forces are pointing downwards. So TOY is going to be equal to positive Fg center of mass plus Fg mass minus Ty. Okay, let's put these all together. So I'm going to probably do the same thing I did last time. So mass Cm plus mass M, factor out G, minus T sine theta. That's what Ty is equal. Okay, let's put our values in. So bracket 110 kilograms plus 10 kilograms. Oops. Bracket 9.880 meters per second squared minus 736 newtons sine 60 degrees. Oops. 60 degrees. Okay, and that equals, and I'm going to put this right up here. Okay, equals. So let's see what that value is. When that's all said and done, 539 newtons, or approximately 540 newtons. Okay, well, now we can find our resultant force tau, or not tau, but TO, excuse me. So let's put that in red. So TO is going to equal to the square root of TOX squared plus TOY squared, square root, and so we have 368. Don't know why the pen's writing weird. 368 newtons, square that, plus 539 newtons, square that, and this is going to all equal 653 newtons, or approximately 650 newtons altogether. So now we have the tension, or the torque. Did I say torque? Because the torque would be the reverse. We have the force TO on the point O. Now, to determine theta for that point, theta is going to equal arctan, and it'll be our parenthesis 539 newtons over 368. I need to write that better. That just does not look good. Let's fix this up. This does not look good. Fix that up. Okay. Okay, now let's choose something. Let's choose orange. Okay, so theta is going to equal tan, or arctan, and let's start that again. 539 newtons over 368 newtons. And that's going to give us 55.7 degrees. So 56 degrees as our angle for the force at TO. Okay, the resultant force. Okay, run this video slowly if you need to. Keep studying physics and don't keep giving up on this stuff. It's good. All right? Till next time. Bye.